Okay.
Okay.
So welcome everybody to our Gamma seminar. And this week, Xavier Rivas will talk about symplectic mechanics. So, Xavier, the floor is yours. Go ahead.
Thank you, Javi. Yeah, as you said, I will be talking about symplectic mechanics, but not only that. As you can see in the outline here, I will also cover. I'll try to cover time-dependent systems, not also symplectic ones. But well, we'll begin with symplectic mechanics, of course. Of course, I will rely on everything you said during your lectures on symplectic geometry and symplectic Hamiltonian systems. So the core of this mini course will be section 3 on Lagrangian mechanics. Although I will say some things about symmetries and conservation and conserved quantities in symplectic Hamiltonian systems that you did not cover. So maybe it will help. Okay, so first of all, I will very briefly summarize what Javi told us in his lectures about symplectic geometry. So what is a symplectic manifold? A symplectic manifold is a pair, M omega, where M is a smooth manifold, and omega is a symplectic form. What a symplectic form? A non-degenerate closed-to form. Okay, these have several implications. For instance, every symplectic manifold is even dimensional, as Javi proved. Of course, all manifolds are orientable since this is a volume form on M. And we have some structures attached with, like, for instance, this isomorphism of vector bundles, which is just contracting with the symplectic 2 form. This is an isomorphism of vector bundles, and in fact, this induces an isomorphism of modules between the module of vector fields and the module of one forms. Of course, symplectic geometry, you can think of it as a counterpart of Riemannian geometry. You can think, oh, it should be similar because you have a 2 tensor. This time it is not symmetric, it is skew-symmetric, but it's okay. It should be similar. Well, it's not. It's not similar at all. Because, for instance, we have this Darboux theorem, which says that actually symplectic structures are quite rigid, are so rigid that every symplectic manifold is locally diffeomorphic to a cotangent bundle. This is essentially what Darboux theorem says, that we have these coordinates, Q and P, so that the symplectic form locally looks like this. So symplectic manifolds are quite rigid. I mean, they are not as rich as Riemannian manifolds. We have additional structures, of course. Every symplectic form on a manifold induces an, as I said, an isomorphism flat, and also to every function f in that manifold, we can associate a unique vector field, which will be called its Hamiltonian vector field, by means of this map here, just computing its differential and then going back with the isomorphism flat. So we can define this vector field xf as the inverse by the flat isomorphism of the differential of the form, or what is the same, this thing here. This thing is Hamilton's equation in a geometric form. But there are a couple of things that we must take into account, and this is quite important. This thing here, this map that we have defined, which relates to every function a vector field, is neither surjective nor injective. So two functions may lead to the same vector field. And of course, there are vector fields which are not the Hamiltonian vector field of any function. Okay, this is important. Okay, so in every symplectic manifold, we have a Poisson bracket. What's a Poisson bracket? A Poisson bracket is a bilinear map satisfying some properties that Javi, did you talk about this? Yeah, I think you defined the notion of Poisson bracket. But yeah, anyway.
But you can repeat it.
Yeah, I will in the next slide. I will, don't worry. But in the particular case of symplectic manifolds, we can define a bracket like this, just contracting with the symplectic form the Hamiltonian vector fields associated to the two functions it is operating in. Locally, what does it look like? In the root coordinates, it has this expression, and in particular for the root coordinates, we have these relations here. Okay, so the Poisson bracket of 2q's is 0, of 2p's is 0, and 1q, 1p is just the Kronecker delta. This Poisson bracket has many properties, actually defining it. What is a Poisson bracket? A Poisson bracket is something that satisfies these properties. It has to be bilinear, it has to be skew symmetric, and it has to satisfy the Jacobi identity. So in our case, in the symplectic case, our Poisson bracket turns the ring of functions into a Lie algebra, satisfying these properties. Also, we have that the Poisson bracket of two functions is just the Hamiltonian vector field of one of the functions acting on the other. Be aware of the sign. There's a sign here, depending on which one you take first. This is because of the skew symmetry. And also, this Poisson bracket allows us to define an anti-homomorphism of Lie algebras relating the functions and its Hamiltonian vector field. And this is an anti-homomorphism. As you see, the Hamiltonian vector field of the Poisson bracket of two functions is just the Lie bracket of the two Hamiltonian vector fields reversed. That's why it's said that it is an anti-homomorphism, because they are reversed.
May I have a comment?
Yeah, sure.
Normally, the thing is that depending on the way you define the Hamiltonian vector field, it turns out that that is an anti-homomorphism or a homomorphism. So
Exactly. If we define it with a minus sign here, as Javi says, then it is a homomorphism, not an anti-homomorphism.
Mathematicians love the minus because they want the second map to be a homomorphism. But in geometric mechanics, in physics, normally the definition we use is that. That's all. It's I mean, it seems to be a stupid thing, but when you have to work with someone, it's a problem, let us say this way, because you have to check that every sign at every place is correct.
Yeah, many of us have had to check a paper from the beginning because there was a sign problem, and well, where is it? It's always here.
Yeah,
it's always in the convention.
one of the possibilities.
Yeah, and in addition, sometimes in some papers you need it to be a homomorphism because you need it, so you have to redefine everything. So you do not always work in the same way. That's confusing, but well, it's okay. This Poisson bracket, this is interesting. I will not be using it, but I wanted to give you this property. You can extend this Poisson bracket to one forms. Okay, and if you do it like this is very simple. I mean, you only have to take the one forms back with the flat isomorphism to vector fields, compute the Lie bracket, and contract it. In this way, you obtain a Poisson bracket for one forms, and they are related like this: the Poisson bracket for functions and for one forms. So the differential enters inside the bracket. It's just a curiosity, but I think it's interesting. Okay, now we will begin with mechanics, now that we have reviewed the basics on symplectic geometry that we will be using. And I will take a more physical approach, at least at the beginning. Then, of course, we will do it. We'll do it in a mathematic way. But this is physics. Actually, you can think of it as an axiomatic way of approaching Hamiltonian mechanics, because I will not be covering any variational principle. And since I want to skip that variational approach, I will take an axiomatic approach. So we will have several postulates. We will assume them to be true, and then we will construct all the mechanics. So these are the postulates on Hamiltonian mechanics. First of all, the state space, the phase space, will be a symplectic manifold. I introduced here the pre. In principle, I will not be talking about pre-symplectic geometry and singular systems. I will say some things at some points, and I will give a couple of, I think, interesting examples of pre-symplectic systems. But, well, I wanted to introduce it, but most of the time they will be symplectic, at least by now. Second postulate, the observables are just the functions on that manifold. Okay, so the observables, the physical magnitudes of related to a mechanical system will be functions. Third postulate, the dynamics will be given by a function, a particular function called the Hamiltonian function. And this function has all the dynamics of this system. And finally, we have the last postulate, the fourth, which says that the dynamical trajectories of the system are the integral curves of the Hamiltonian vector field associated to this function h. That is the vector field xh, which is a solution to this equation. So it is the Hamiltonian vector field associated to the function h. And, well, the integral curves of this vector field, of course, are the solutions to this equation, which is just the same equation as before, but in this case for integral curves. So this vector field will be called the Hamiltonian vector field. And these equations 1 and 2 are Hamilton equations for vector fields and for integral curves.
Xavi?
Yes.
Yes, maybe you can explain a little bit more in detail what equation 2 means, because when you have the integral, I mean, when you have a cube, the left-hand side defined only on the image of the cube, so it's a little bit.
Yeah, okay. I will explain it right away. So we have here a piece of the real line, and we have our manifold M, and this is a curve gamma, which is somehow it's the trajectory of the system. Okay, what does gamma prime mean? This is the canonical lift of a curve to the tangent bundle of the manifold M. Here we have this canonical projection. So the curve satisfying this, making this diagram commute, where here we have a vector field. This curve here is the canonical vector field, or the integral curve of this thing. And it satisfies this thing here. Okay, so this lift here, it's just this. I mean, it's just the curve lifted to the tangent bundle.
Let us say this way, if you allow me to say. If you have gamma in coordinate, you have the coordinates of gamma, and gamma prime, the lift is just the partial derivative of the coordinates in terms of the parameter. It's just, yeah, indeed.
This is
the canonical. Yeah.
Exactly. Whoa, this is too big. What happens? Oh, okay. Now, great. So this is what gamma prime means. Okay, it's just the lift of a curve to the tangent bundle, and locally it looks like this. Okay, so you can think of it as the velocity of the curve somehow. Okay, so what is a symplectic Hamiltonian system? A symplectic Hamiltonian system is just a symplectic manifold with a Hamiltonian function. And of course, given a symplectic Hamiltonian system, we have a unique vector field satisfying this equation here. This vector field is called the Hamiltonian vector field of the system. So locally, what does all this mean locally? So in the Darboux coordinates, we can compute the differential of the Hamiltonian. This looks like this. And we can take a generic vector field in the manifold M, which looks like this. If we impose this condition here, you only have to compute the contraction and equate the terms with the differentials, what goes with differential of Q and what goes with differential of P. And you obtain these two equations. which are just Hamiltonian equations in local coordinates. And so the Hamiltonian vector field locally looks like this. This is the local expression of the Hamiltonian vector field. And of course, its integral curves, what do they satisfy? They satisfy this thing here. If you pick a curve in M and you impose it to be an integral curve of this vector field, you obtain that it satisfies this system of equations, which are, of course, Hamilton's equations that I think you all know. I mean, everyone more or less has seen this in a physics course, I hope.
May a remark?
Yeah, sure.
I mean, the Hamiltonian equations are standard in literature, quite standard. But the thing that is not very well known is that sometimes when one has a dynamical system, someone has a physical system with certain differential equations describing it, sometimes someone wants to describe it in terms of a Hamiltonian. So it appears the so-called inverse problem. You have a certain system whose trajectories are described by means of the integral curves of a vector field, and you want to find out a Hamiltonian and a symplectic structure, turning the vector field into a Hamiltonian one. Okay, it's a little bit complex. Here you have a vector field, you look for the solutions. In many cases, you have the solutions and you want to obtain the Hamiltonian. It's fun to show that for every vector field, which has a point where it does not vanish, you can always find a symplectic structure and a Hamiltonian, turning the equation for the integral curves to be the Hamiltonian equations for a certain Hamiltonian. This is fun. But if the vector field has a zero, has a so-called singular point, it does not. This is a quite fun thing, that it turns out if you have a stability point for a vector field, it can be impossible at all to look for a certain symplectic form and a certain Hamiltonian turning it into a Hamiltonian vector field. And this has to take into account, well, let us say that the thing is when you have a Hamiltonian, normally the evolution leaf and volume invariant, maybe you will talk about it. But if you have certain vector fields with a stability point, normally they have all so-called sources or points where the dynamics goes to a certain point. And in no way these vector fields allow for the conservation of a volume. So in that case, there exists no symplectic for a field like that. It's quite interesting that certain vector fields cannot be studied this way. Thank you.
Thank you, Javi. Your comments are always very interesting. Okay, so now let us see some examples. We will begin with the maybe the most classical one, the harmonic oscillator. How can we describe in a Hamiltonian symplectic way the harmonic oscillator? Okay, so we have to take as a configuration manifold just the real line R with coordinate Q, and the phase space will be, of course, its cotangent bundle with adapted natural coordinates QP. And in this cotangent bundle, we all know we have this canonical symplectic form. Okay, so what's the Hamiltonian describing the harmonic oscillator? Well, the Hamiltonian is actually this one. No, it's not. I forgot this too here. Okay, now this is the Hamiltonian of the harmonic oscillator, where K, this is a constant of the oscillator. If we write the Hamilton equations for this Hamiltonian, beginning with a generic vector field, here imposing Hamilton's equation, we obtain that this is the Hamiltonian vector field, and of course its integral curves satisfy these equations, and combining them, we obtain this equation here, which is indeed the equation of a harmonic oscillator. So this, in principle, only, let's say, gives us a fancy way of describing things, but it gives us much more. For instance, I will begin now talking about symmetries, conserved quantities, and all this, and we will see how the geometry is doesn't only give a fancy way of writing things, but it also may give you a deeper understanding of the systems. And so you can deduce things of the system, which would be, let's say, less obvious if you ignore all the geometry involved. Of course, the harmonic oscillator has been very studied, and we will not be reinventing the wheel, but you can always apply geometry to other systems. It might illuminate you somehow. Sometimes you discover geometries and I mean behind the curtains, let's say. So let us begin talking about conserved quantities, but before that, we need to define what's the evolution of an observable. Okay, so given a Hamiltonian system with Hamiltonian vector field xh, we already have it. What's the evolution of an observable? Okay, the evolution of an observable should be the evolution of the function along an integral curve of that vector field. So this is the evolution, which is obviously this thing here. And using the Poisson bracket that we introduced 15 minutes ago, we can write it this way. So in the root coordinates, the evolution of an observable along the integral curves of the Hamiltonian vector field looks just like this. So what will be a conserved quantity? Okay, a conserved quantity will be something which is conserved along the solutions. I mean, along the integral curve of the Hamiltonian vector field. So satisfying this thing here. Okay, a first comment. Of course, the Hamiltonian function h is a conserved quantity. So the energy, let's say, the Hamiltonian is closely related to the energy. The energy is conserved if the Hamiltonian does not depend explicitly on time and this kind of things. So Javi was, in his course, he talked about symmetries and he told us how to reduce by symmetries, but now we are going to say some more things about symmetries. And actually, we will talk about a couple of different types of symmetries and discuss which of them gives us conserved quantities. That will be Noether's theorem. Well, let's begin with dynamical symmetries. I mean, what is a symmetry? Symmetry, in an abstract way, is a transformation preserving something, okay? What? Well, in this case, a dynamical symmetry will be a symmetry preserving the dynamics of the system, that is preserving the Hamiltonian vector field. That's a dynamical symmetry. So the dynamical vector field must be invariant by this transformation. Of course, if we have a dynamical symmetry, its inverse, it is also a dynamical symmetry. Okay, actually, a dynamical symmetry, a diffeomorphism is a dynamical symmetry if and only if it transforms integral curves of the Hamiltonian vector field into other integral curves of the Hamiltonian vector field. But this is the approach with diffeomorphisms. But sometimes we are more interested in the infinitesimal version. I mean, we don't need the diffeomorphism. We only need to know how it acts locally. So we define what an infinitesimal dynamical symmetry is. This is the infinitesimal version. An infinitesimal dynamical symmetry is a vector field Y whose flow is made of dynamical symmetries. What does that mean? Well, it means that this Lie derivative has to be 0. So that the infinitesimal dynamical symmetry preserves the Hamiltonian vector field. Fun fact, the set of infinitesimal dynamical symmetries are a real Lie algebra with a Lie bracket of vector fields. You can prove that. It's quite easy. Well, dynamical symmetries have some good properties. They transform conserved quantities into conserved quantities. So if we have a diffeomorphism, which is a dynamical symmetry, and we have a conserved quantity F, then this composition here, or this pullback, which is the same, is also a conserved quantity. And the same with vector fields. If we have an infinitesimal dynamical symmetry, this Lie derivative here is also a constant of motion, or a first integral, or a conserved quantity. These are all synonyms.
And this proof you mentioned just follows from the application of the Jacobi identity here, yes?
Yeah,
and that's
that's
all.
right. Yeah, exactly. This is just an exercise. Yeah. Okay, but dynamical symmetries are okay. They have nice properties, but they don't give us conserved quantities from a Noether's theorem in general. So we have to define, let's say, a stronger notion of symmetry. So we will introduce Noether symmetry, which are the symmetries preserving what? Well, preserving the symplectic structure and preserving the Hamiltonian function. Okay, and the same with the infinitesimal version. I mean, this is for diffeomorphisms. We can also define it for vector fields. So an infinitesimal Noether theorem will be a vector field preserving the symplectic structure and preserving the Hamiltonian function. And these are the symmetries that will allow us to find conserved quantities. So knowing what symmetries does the system have, this will allow us to find first integrals and thus reduce the system using a Marsden-Weinstein method or whatever. But just a first fact before that, Noether theorem are dynamical symmetries. You can check it. That's quite easy. And again, Noether theorem close a real Lie algebra with a Lie bracket. Again, so are a subalgebra of dynamical symmetries. Okay. Now, first result. This is a proposition, but it's more like a lemma because this will be useful to prove Noether's theorem. If we have a vector field which is an infinitesimal Noether theorem of a Hamiltonian system, for every x, there's a neighborhood, an open neighborhood around it, and a one form in that neighborhood. There exists a neighborhood such that if theta is a symplectic potential of omega, this symplectic potential always exists locally because the symplectic form is closed, so locally it is exact by Poincaré's lemma. So this symplectic potential, we can always find it, satisfies this thing here. Then in this situation, there exists always this function theta y satisfying this. And in addition, if fy is a local Hamiltonian function, I mean local because it satisfies Hamilton equation, but only on the open set U of the Noether symmetry Y, that means that this satisfies Hamilton equation in U, then we have this thing here. Of course, up to an addition of a constant function. Okay, so with this, let's say, technical result, we can state and prove actually Noether's theorem. And what does the Noether's theorem say? It says that if you have a Noether theorem, you have a conserved quantity. And conversely, if you have a conserved quantity, you have a Noether theorem. So, more concretely, given a Hamiltonian system, if y is an infinitesimal Noether's theorem, its local Hamiltonian function, fy, is always a conserved quantity. So this is satisfied, where this fy is the fy that we found in the previous slide here. Okay, and conversely, if we have a conserved quantity, its local Hamiltonian vector field, yf, will be an infinitesimal Noether theorem. Okay, do I have time to prove it? Well, I will try. Okay, we have this thing here because fy satisfies this, and thus computing this Lie derivative, I mean, it's just a matter of Cartan calculus, you find that this Lie derivative is 0. Conversely, if yf is locally Hamiltonian. It is. We have that it preserves omega. Okay, but this is not enough to show that it is a Noether theorem. We also need to check that this is 0, but it is also 0. Again, it's a matter of Cartan calculus, using all the things we know, just an exercise to check that this is again 0. Of course, the hard work is made proving this lemma. Okay, this is where the work is, and I skip it because it's, I mean, a bit longer. But here are the ideas. I mean, associated to every concept quantities, we have a Noether theorem and the converse. Okay. And there is more. I mean, Noether's theorem doesn't close the problem of finding symmetries, because although in general there is no way of finding conserved quantities from not Noether's theorem, there are some particular cases where you can. Okay, so for instance, pick an infinitesimal dynamical symmetry, just dynamical, preserving the Hamiltonian vector field, such that this is not 0. Okay, then this thing here is a conserved quantity. Actually, if it is 0, it is again a conserved quantity, but it's a trivial one. Doesn't have any interest. Okay, the interesting case is when this is not 0. And the proof is, well, just computing this thing here, and using the definition of the Lie bracket, you can check it. Okay. Now an example, because we will see how Noether's theorem allows us to prove that the angular momentum is preserved, is a conserved quantity in Kepler's problem. So in order to describe Kepler's problem, we have to consider a mass m under the action of a central force. Of course, we know that this motion lies in a plane, so our configuration space will be R2. We will take polar coordinates in R2, centered at the origin, where is the force. Okay, so we will consider this case. If not, you can always change the coordinates so you can achieve this. Then what's the phase space? The phase space is this cotangent bundle. We will take these coordinates in the cotangent bundle, the radial coordinate, the angular coordinate, and the two momenta. The symplectic form, of course, is this one. This is canonical. And the Hamiltonian function that we have to consider is this Hamiltonian here. As Javi said, it's not always obvious how to find a Hamiltonian function associated to a system. This is not always clear. I mean, in mechanical systems, usually it is the energy, but in more complicated systems, it may not be trivial at all. This is the inverse problem. And it is especially interesting in Lagrangian mechanics. We have here an expert, right, Jordi, in whispering to the Lagrangians. Actually, Jordi is very good finding Lagrangians to, I mean, random PDEs or ODEs that you can imagine. So consider this Hamiltonian here. Trust me, this Hamiltonian describes Kepler's problem, where this K is a constant. Okay, now we take a generic vector field. This is the same as before. Take a generic vector field, impose Hamilton's equations. This is only a matter of linear algebra. There's no ODEs or PDEs yet. And we find that the Hamiltonian vector field is this thing here. Okay, this is the Hamiltonian vector field. What are its integral curves? Its integral curves satisfy this system of equations. These are ordinary differential equations, and you can combine them and find Kepler's equations. Okay, I will not do it, but you can try combining them. So let's talk about symmetries of this system. This symplectic form has a symplectic potential. This is something that we need in order to make the theorem work. And this vector field here, this is a Noether symmetry. This is quite easy to check because the Hamiltonian and the symplectic form are invariant through the action of this vector field. And in addition, also it preserves the symplectic potential. Then according to Noether's theorem, we have an associated conserved quantity. This conserved quantity is nothing more than the angular momentum. So the angular momentum is preserved in Kepler's problem, and we can check it just with Noether's theorem. This is very easy, very trivial. In this example, we all know that the angular momentum is preserved, but this might not be so obvious in other systems. Because it may be easy to find a symmetry, and Noether's theorem will automatically give you a conservation law. Okay, this finishes the symplectic Hamiltonian part. Now we will begin with Lagrangian.
May I have a last remark? Yes, the last thing, because at the very end you didn't do it, and maybe it's important that when you have symplectic Hamiltonian systems, there is something that it's very important to study the dynamics of this symplectic Hamiltonian system. And this is the fact that since a Hamiltonian vector field leaves the symplectic form invariant, it also leaves invariant every exterior product of the symplectic form with itself. In particular, I said in my talk that there is a volume form associated with every symplectic form, and it turns out that Hamiltonian systems, they leave this volume form invariant. That means that the evolution of every Hamiltonian system leaves this this form, invariant, and this idea of volume invariant. So if you pick a certain region of a certain point of your symplectic manifold, and you evolve every point of this volume according to time, okay, the volume of this region must be constant. And normally this is interesting to study the evolution of systems. And it also explains why certain dynamical systems cannot be described by means of a symplectic form. Because, you know, if you have a certain dynamics that contracts every point in a plane into a point, you can see that at the very end, this cannot be symplectic, because whatever the volume form is, it will be not preserved. The volume will not be preserved, yeah? So this is the so-called Liouville theorem, yeah? This is one thing. Another thing is that the Kepler problem, you used to take the constant with a fixed sign, that is due to physical reasons, yeah? And well, let us say that these are the most important things I could tell now, because all the relevant things for Hamiltonian system, they need more comments than the development something. Thank you. That's all.
Okay. Yeah, you're right. This is actually very interesting, the thing that the Hamiltonian vector field preserves this symplectic volume, because sometimes you have systems which do not preserve this symplectic volume. Actually, many people here work on contact mechanics, and in that case, you deal with systems which, of course, do not preserve the volume, because many times they are going to collapse to a point. For instance, anytime you introduce a damping, the system just goes to the origin. And in that case, of course, you do not have a symplectic underlying structure. You have other things. Okay, now let's turn to the Lagrangian side. This is interesting. I mean, there are many differences and similar things between Hamiltonian and the Lagrangian parts. I will try to stress some of them. Somehow the Lagrangian part is more complicated somehow. I think it's trickier, and I will try to tell you why. I'm not sure if I will be able to do it today, but I think I can tell you what the tricky part is. And the trick is that in the Hamiltonian side, you have this thing here. You have a cotangent bundle. And from here, you have a canonical symplectic form. This form is canonical. Okay, so if we have a Hamiltonian function, you can always write this equation. And this equation is very nice because, look, this is all geometry. There's no dynamics here. Okay, here we only have geometry, the omega. And here we only have dynamics. There's no geometry here. We only have dynamics. So everything is it's separated somehow. In one side of the equal, we have geometry, and on the other side, we have dynamics. This does not happen in Lagrangian mechanics, and I think this particular fact messes everything, because in the Lagrangian side, we will not have momenta, we'll have velocities. And since we'll have velocities, we'll be working here in the tangent bundle. You'll say, oh, the tangent bundle is easier because it's easier to visualize and everything, but it's not true. It's trickier, actually, because here we do not have a canonical symplectic form. We simply do not have a canonical symplectic form, and we will have to find some symplectic forms. But how we will do it? We'll do it with a Lagrangian function. And you could say, oh, okay, in the Hamiltonian side, we have the Hamiltonian function. In the Lagrangian side, we have the Lagrangian function. Yeah, but this is trickier because from the Lagrangian, we will build the Lagrangian energy, which actually this function will be taking the role of the Hamiltonian. This Lagrangian energy will take the role of the Hamiltonian. But from the Lagrangian function, we will build a symplectic form. Well, it will not always be symplectic, but since the Lagrangian is regular, you will be able to do it. If the Lagrangian is not regular, then crazy things happen. I will try to just tell you some of them. But the thing is that the symplectic form depends on the Lagrangian. So in the symplectic form, you already have dynamics because the dynamic information is in here. And when you write, you say, okay, I have a symplectic form and I have an energy, so I can write this thing here. I can write this thing here. There's no problem. And you're right. Actually, these are the Lagrangian equations. But see, here we have dynamics, okay. But here we have not only geometry, we have geometry and we have dynamics. And this messes everything, I think. So be careful in the Lagrangian side, because it is not as easy as it seems, okay? The problem with the Lagrangian side is that in order to introduce this form omega L, which in favorable cases will be symplectic, I will need to introduce several structures in the tangent bundle. This is what I will begin to do today, and I will finish it next week. So, in the tangent bundle, what do we have in the tangent bundle? We have several natural structures. Let's begin. The first one, the vertical subbundle. What's the vertical subbundle? Okay, we have a manifold Q with coordinates Qy, and we have this natural projection from the tangent bundle to the original manifold. Of course, this tangent bundle has, for this tangent, this canonical projection has a tangent map, this map here. And with this map, we can define the vertical subbundle. What's the vertical subbundle? It's just the kernel of this tangent map, okay? So the vertical subbundle at a point, it's just the kernel of this tangent map here. We will see it in coordinates, okay? But from now, it is just this kernel. And of course, we can construct the bundle just with the union of all these vertical subspaces. The sections of this subbundle will be called vertical vector fields and will be written in this way. So vertical vector fields go from TQ to TTQ, okay? But not TTQ, but subbundle in here, okay? Okay. So actually, vertical vector fields go this way. Okay, so our vector fields in TQ, not in Q, in TQ. Okay, which just with this projection just go to 0. So somehow you can think of them as tangent to the fiber. Okay, but take this with caution. But they are just tangent to the fiber. So locally, what does it look like locally? If we have these natural coordinates, natural adapted coordinates in the tangent bundle, the local expression of a vertical vector field looks like this. So this is what I meant with tangent to the fiber. I meant that it only has component on the fibers. Okay, it only has components on the velocities. And of course, the vertical vector fields are locally spanned by this family of vector fields. Okay, now let's see what properties does this have. We'll try to give another interpretation of the fibers of this bundle here, okay? So for every Q in the manifold Q, consider the n-dimensional vector space, this tangent space here. Of course, we have this natural immersion. We can introduce a tangent space in the tangent bundle. This is very natural. Okay, of course, note this thing here. If you introduce a tangent space in the bundle and then project it, this is constant, equal to Q for every vector field, of course, in this tangent space. Okay, this is constant. So its tangent map will be 0, right? Its tangent map has to be 0 because this is constant. So the image of the tangent map to this inclusion is inside this kernel, but this kernel is just the vertical subbundle. But this JQ is an immersion. So this dimension has to be the same as this. And this is n. And this is actually the dimension of the vertical subspace, of the vertical subbundle at a point. Okay. So this vertical subbundle is just the image of the tangent map to this inclusion here. Okay. Maybe this can help you to imagine what this vertical subbundle is. I'm not sure if you are all familiar with the structures of the tangent bundle. Maybe Javi, you can tell me. I mean, PhD students and
no, I don't think so. They could have some kind of structures and things of these. I mean, the vertical subbundle, maybe the post-vertical lift, kind of. I have my doubts.
Okay, so note that this.
But if you continue with all the structures which are natural, I think that.
Okay, great. But just note that this thing that I did here for tangent bundles, this is not only for tangent bundles. This is actually for vector bundles. Okay, you can define all these things in vector bundles. But I will be focusing only on the tangent bundle because it's the vector bundle that I need. Okay. Of course, there is again a theory on double vector bundles. This bundle here is a double vector bundle because it's doubly a vector bundle. There's a lot of theory about these objects. You can check it. It's very interesting, and many people.
If you allow me, it's a worse speciality.
Yeah, I know. That's why I'm saying it. That's why I'm saying it. Tulsi triples and all this, putting asterisks everywhere. And of course, in Warsaw, there's a lot of people interested in this.
Like also the case when the Lagrangian functions are not regular. It's also
exactly. That's where Tulsi triples are interesting. Of course, not everyone studies Lagrangian singular Lagrangian with Tulsi triples, but it is an option.
And one curiosity is that even Tulchiev once he saw, because he passed away lately, someone dealing with his theory, he used to say that you are paying attention to the things that are not important. But this is usual, the way Tulchiev behaved.
Yes. Okay, so now we have the vertical subbundle. Okay, so with the things that we saw, we see that this vertical subspace, the vertical subbundle at a point QU. Look, that I'm not saying I could write just this. Okay, I could write this, but I want to stress the Q because this is a point of the tangent bundle. Sometimes when I began studying all these things and reading them on my own, I was all the time confused that sometimes I had a vector field. I didn't know if it was a vector field on Q or on TQ, because actually when you have a vector field on Q, Okay, it is a map here, so it takes values in TQ, and then you have a vector field on TQ, and then you are living here, and this was always a mess. So I'm trying to stress always that these are subspaces of the tangent bundle. I mean, of the tangent space at a point of the tangent bundle. I mean, it's more complicated to say than to think it, but okay. This vertical subspace here is naturally identified with this. How? With the isomorphism that we studied. Okay, with this isomorphism here. Okay, in addition, since this is a vector space, this can be canonically identified with this. How? With the directional derivative. Okay, with the directional derivative, you can identify a vector space with the tangent space at any point of that vector space. Okay, this can be done with the directional derivative. So we can identify this vertical subspace actually with a fiber of the original manifold Q. Okay, of the tangent bundle of the original manifold Q. So in other words, another definition of the vertical subbundle. It is just the pullback bundle of this with this map. Okay, this construction of pullback bundles is generic for vector bundles, and I'm not sure if for fiber bundles in general. Maybe, Javi, you know?
Sorry, once again?
Yeah, you can pull back any fiber bundle with a map or only vector bundles. I'm not sure of this.
Normally it's done with vector bundles,
Yeah,
but I guess that you could do it with any bundle.
If anyone is interested, you can check this book. Here
Yeah,
you will
keep
find
going.
anything you need about bundles.
I mean, about bundles for sure. For other one, I should check it. Okay, that's. I mean that for vector bundle for sure you can make
Yeah.
that, but for general ones,
Well, it deals with general bundles at the beginning. Yeah, I know. I used it to look for problems for a for a differential geometry course I gave. Okay, so you can define the vertical subbundle as the pullback bundle with this map here.
Excuse me, what is this book? Because you just wrote the surname, I suppose.
It is geometry of jet fields or of jet bundles. I am not sure of the title. The author is David Saunders. And I think it's jet
geometry
bundles.
of jet bundles, I guess. I mean,
Okay.
if you write bundle Saunders in Google, it will appear.
I have it here. I have it here. Great. Yeah, the geometry of jet bundles.
Yeah, it is.
Here.
So I'm looking
This is the
for
book.
it.
Okay.
I mean, it has something like 400 citations, so it comes up very easily.
And well, I was going to check new bundles from all, page 20. Just give me a second. I think, yeah, you can define the pullback. Yeah, you can define the pullback of a general fiber bundle. As
Okay, yes, because this pullback, it's just categorical construction, yes, and it can be done on the category of sets. And then restricting our morphisms to the morphisms, for example, of topological spaces gives us this construction.
Okay.
I mean, you can do in different settings from a categorical way. The problem is that when you require a certain pullback to be in a categorical way, you have to ensure that it must remain inside the category. So, truly speaking, you are a little bit cheating because what you want to define is inside the requirements of your definition. I mean, in topological, yeah, you can do, but in other types of bundles or depending of the set, in the categorical way, you know, morphisms are demanded to respect all structures, okay? The question is what you have to require in each case to do so. Do you know what I mean?
Okay, I understand. For example, given, in fact, any category that is interesting for us, it can be mapped to the category of sets just by the forgetful factor, and then we can construct this fiber products on sets. Yes, but then we don't know if these two maps from this fiber product are still
we
in our
require
category.
Additional
So
condition
they
of
are surely
category.
they are surely in. That's surely true for the topological spaces, but not for the general.
Yeah. And that's the point. That's
Okay.
We have to be careful with that because in category theory you are assuming more than you have some additional assumptions. But sometimes the question is that these assumptions, which are and if they behave, they are satisfied.
Okay, so thank you for the remark.
It's true. You have to be careful because you can lose a structure doing this kind of thing, as Javi said. Okay, so what time is it? It's 10. Okay, I will talk a little bit about the vertical lift because I just introduced the vertical subbundle. So we want to take things to the vertical subbundle, and I will stop here then, okay? So we have this isomorphism of vector spaces. Let's see. We have a vector, a tangent vector at a point of a manifold Q. And by means of the directional derivative, we can take it to the vertical subbundle, where this thing here is defined for every function f acting on a function f that's a vector, something that acts on functions, like this, just like the directional derivative. So this vector here that we have defined, seeing how it acts on functions, this is the vertical lift of the vector v, a vector on Q, to a point Q, EU, and this map is actually the vertical lift. This map allows us to lift vertically functions to the vertical subbundle. In coordinates, what does it look in coordinates? So taking natural coordinates on the tangent bundle, if we have a vector on the base, a vector, this is wrong. This vector is in Q, in a point Q, then its vertical lift looks like this. And of course, this vertical lift can be extended to vector fields. So from a vector field on Q, we can lift it to a vertical vector field on TQ, okay? In such a way that if this is a local vector field on Q, its vertical lift, this thing here, the image with this lambda v, we will denote it just by xv, is this thing here. And this, as you can see, is a vertical vector field on TQ. So next day, I will begin talking about the rest of the natural structures of the tangent bundle, namely the canonical endomorphism and the Liouville vector field. These two objects will be the ones that will allow me to define these objects. I will show you just in a second, very fast. You will not see anything, but I will show it. This J, this thing here, and this delta, which is a vector field. The other thing is an endomorphism. This is a vector field. With these things, I will be able to define, wait a second, this thing here. With this J, I will be able to define this omega L. And this, I will construct it with this J and with a Lagrangian function. And on the other hand, I will be able to build a Lagrangian energy using this Liouville vector field. And these will be the ingredients in order to write the Hamilton equation, but in the Lagrangian side. So if the Lagrangian is good enough, that is, it is regular, this omega L will be a symplectic form, and we will be able to take this energy as the Hamiltonian and write Hamilton equations in that Lagrangian symplectic system. And the equations that we will obtain will be the Euler-Lagrange equation that I assume that maybe you have seen or maybe you haven't, but for sure you will next day. So are there any questions or comments or anything? I was quite optimistic. I thought I could cover all Lagrangian mechanics, but I'm afraid.
It used to happen. I was thinking about it from the half of the talk that you will not finish today. So just one remark, if I may, if no one else wants to say.
Yeah, I was worried because I thought, okay, I will teach Hamiltonian and Lagrangian the first day. And what will I do the second? Well, I will do time dependent and I will do contact. What will I do? Okay, now I know I will do Lagrangian mechanics.
It's typical. Well,
But
one thing, Xavi,
yeah,
you said it, but it's one remark. I will say the same you said, but in another way.
okay.
In the cotangent bundle, there is a canonical symplectic structure, and that's why mathematicians love it. But in a tangent bundle, there is not. Okay.
Yeah, that's right. That's what I said.
The other thing, yes, is the remark is just by repeating more or less what you said, but in another way, is that mathematicians don't like the symplectic structures on the tangent bundle because they are defined by means of something that is not canonical. It's some function, but this is some function. I mean,
and it's even worse because not every function will give you a symplectic.
Yeah, and you don't know if there will be a function doing the job. So it can, it can. There is this is another thing because you can say, well, the tangent space, the tangent manifold to a manifold, and the cotangent, they look very, very similar, yeah. And one thing that may make some kind of natural diffeomorphism between them, but no. I mean, if there was some canonical diffeomorphism between the tangent bundle and the cotangent bundle to a manifold, they could be for every tangent manifold a canonical symplectic structure, and there is no such.
There is not.
So tangent and cotangent bundle, they look very similar. Everyone thinks that they are pretty much the same, but they are pretty much different.
And it's fun because there are. Sorry. Maybe I will put the stars in the wrong places, but if I am not mistaken, there are canonical isomorphisms between these things.
Yeah, but
I think that even with this thing here we have canonical isomorphisms.
Yeah, but you are fixing the base manifold.
Yeah, but you do not have a canonical isomorphism here. You have canonical isomorphism here, and this is complicated. But this, here you don't.
These things, what you wrote, they are related between them. But somehow you are fixing the manifold in which you are defining the isomorphism between tangent and cotangent. Yeah, because
that's right. Because here you have Here you have this T star Q and this T star Q. And okay, you define between the tangent and the cotangent, but not of an arbitrary manifold, but a very special one.
It's the point that it is a cotangent one, but not everything is a cotangent.
No, of course not. But
and the first one
it's kind of surprising that here in some complicated things you have and here you don't.
Yeah, but the thing is that those complicated things, they are particular things. That's why it's not weird. I mean, if you look for certain manifolds of a particular type, they will appear certain structures that normally they don't exist. Yeah. So I mean, for me, it's natural that in a particular case for cotangent tangent manifold, you will have certain isomorphism or diffeomorphism between tangent and cotangent bundles because there are particular cases where there are additional structures. But if you put something so general as Q, who knows?
Yeah,
You have an idea about what is going on. That's fun, but you know, it seems to they look very similar, but at the same time, they may be absolutely different. And locally, they are the TQ and T star Q. Locally, they are diffeomorphic. Yeah, they are bundles. They are vector bundles with the same
dimension.
Yeah, but they don't need to how to say.
They are not canonically isomorphic.
Yeah,
they are
I mean,
not canonically.
Locally, you have a vector bundle morphism between them. Yeah, but it's not canonical. And globally, they don't. It does not need to exist. That's the point. That it does not glue together. These local things they don't need to be enough to ensure that there is a global object.
Yeah, you're right. And you said that mathematicians don't like tangent bundle, but
many mathematicians don't.
Yeah, I know, but this particular thing makes it actually, I think, more interesting because it's more mysterious. You don't have canonical things; you have to work your way out. And
yeah, but
there's no God telling you this is the symplectic form. No, hey, that's your problem. Find the symplectic form.
But by the way, there is a comment that sometimes says, some people say that Lagrange equation is some kind of ghost equations because it's a very big, God's equation. I mean,
God's.
That's is like in the Hamiltonian that at the very beginning they have a certain principle to describe the laws of physics by means of Lagrangian approach. And you know, the Lagrangian to describe a mechanical system is a matter of looking for a function. It's an inverse problem, but on the Lagrangian side. And many people wanted to describe, to find a Lagrangian for any mechanical system. The problem is that whether there exists for every mechanical system a way of writing the equation of motions like a Lagrangian principle. Well, the answer is no. There are some conditions yet to satisfy it. But at the beginning, they wanted to put everything into this scheme. Trying to describe everything in a Lagrangian model. But not every dynamical system, not every second order differential equation can be described by means of a Lagrangian principle.
Well, not only second order differential equations, because in the next talk, but I will do a small spoiler. I can show you some first order. Wait. I don't want to spoil everything, but for instance, this system here comes from a Lagrangian. Actually, this absolutely disgusting Lagrangian here, this gives you these equations. And this is very fun because they are first order differential equations. The thing is that these logarithms, once you compute the derivative, they cancel the second derivatives and you obtain first order equations. And this is because this Lagrangian is very singular. This is one of the Lagrangians that do not give a symplectic structure. Actually, the symplectic form they give is this thing here, which is by no means symplectic. Actually, it has a two-dimensional kernel, so it's not symplectic. And you can say, well, what is this system? I mean, this is an epidemic model, but there are other systems which are very well known. For example, Lotka-Volterra, it has this, well, it's even weirder, this Lagrangian here with all these logarithms, and it gives you these equations which are first order. These kind of things, you cannot do it with Hamiltonian mechanics. So in the Lagrangian side, I think you have very interesting things.
I was taking a look at this, and it's quite interesting because the two formulas is presymplectic.
Yeah, it is. And maybe you can even talk to Eva Miranda because this might be.
This is what I was thinking of, because
I know you. I'm not sure it is bisymplectic, but it looks like
presymplectic. I mean, that two form. The problem is that it's not well defined.
No, wait. You are working in here, okay?
Okay, but for
You're
the
working in
differential
here.
equations you heard, okay, because I mean for the
These are
equation
populations.
you had,
You cannot have minus 100 lions in the jungle.
yeah, I mean
These are populations. But if
But-
you admit negatives, well, maybe this is B symplectic or B whatever.
what I wanted to tell you for the very beginning is that this form you wrote downstairs, yeah, and the bottom is close and it's not degenerate, so it's symplectic. So why are you saying that it's
No, it is not symplectic. No,
no,
it is
which space with the velocities?
no, in the tangent bundle. I mean, you have x, y, and x dot
Okay, that's what I was asking in the
dimension 4.
Okay, yeah.
Here, I wrote the kernel.
Yeah. Because
It's
I
the
didn't
same
know what
form.
you meant.
Here I
Yeah.
wrote the kernel.
Sure.
So you should have this thing here too, but you don't.
Yeah. Because I didn't know which space you're working.
Yeah, because I was very fast. I was going very fast. Yeah, because
you know,
this looks like a two-dimensional system somehow, but it is not. It's a four-dimensional system if you think it as Lagrangian.
Yeah,
but the thing is that it is so singular that everything cancels and you lose a lot of things.
because what I meant is that what I was thinking, okay, I mean, when you say presymplectic depends on the space. With these equations, you could do, these equations has sense on R2, on the wall R2. And then is what you said, when you were talking about EVAs, about base symplectic, it could be that this is something like base square symplectic of things of the sort, because normally it's something like a symplectic form, because that could be some kind of symplectic form everywhere away from a certain place where x equal to 0, y equal to 0. The problem is that that is not a submanifold because there is a crossing point and the origin. Yeah. So you should even make some more complicated than base symplectic. But
you can think it in xy with x positive, for instance, and then there you have a submanifold.
Yeah. But you know, it's in that case it could be that that is base symplectic, and you could try to do the whatever. By the way, there is one interesting thing I was taking a look.
Just one thing. It wouldn't be B symplectic. It would be B pre-symplectic because it's singular.
I mean, it depends on how you want to describe it.
No, but I mean in here, so it is Lagrangian.
Yeah, in here that's why I say it depends on where you want to do it, because you could try to explain it. I don't know where you describing all these things Hamiltonian. I mean, if you mean on because this is for the Lagrangian. Well, I don't know. Okay, because I don't know what exactly you mean now.
We will talk about this next day, but I couldn't resist to show you this.
Because I was understanding something different, but I see that here something must be wrong. Okay, so anyhow, it could be interesting because you know what I was doing today was to describe certain dynamical system that cannot be described by means of a symplectic form, because it turns out that they have singular points, yeah. And this singular point, there are sources or sinks for certain dynamics. And it turned out that you cannot describe them by means of symplectic form, but you can describe them by means of a base symplectic form. Yeah, and this is kind of interesting because it says that base symplectic geometry is much more interesting even that Eva and all these people, Guillemin, did. I found some examples where singular points can be described by means of this sort. Indeed, you can see that these all Lagrange equations on the first order you wrote, you will have a certain equilibrium point and 0, yeah? And so
in 0, this is not well defined because you don't have Lagrangian in the 0, okay? But
yeah, but I mean the difference.
Yeah, in the ODE, yes. In the ODE.
Yeah, but I mean, if you define the equations by itself without the Lagrangian, because as I told you, sometimes you have a dynamics and you want to describe the dynamics by means of something, and the Lagrangian is just a tool to describe it. Yeah.
Exactly.
For example, in dynamics, you have the equation of motion for an harmonic oscillator and all this stuff about Hamiltonian Lagrangians and things like that. you know, it's after Newton's equation. You have second-order differential equations. You describe the motion by means of them. And someday one guy says, oh, let us describe this by means of a Lagrangian principle. Yeah, there is a certain function. We can describe the minima with certain conditions. It comes up with the idea that there is a function that describes the harmonic oscillator. Yeah, a particular one. And you start doing this for every mechanical system, and for 10 decades even, you start thinking that every mechanical system, every Newton equation can be described by means of this, yeah, till you find that it does not work at every case. But you know what I mean, that the original thing is that you have your equation of motion, you have physics, and at a certain moment in the history, some guy describes the Lagrangian and says that it can be used to describe physics, yeah? But this is a little bit afterwards.
Yeah, this was Maupertuis and other
all these people and the Hamiltonian principle and things like that. But the original thing, they are equation of motion, Newton equation of motion, second order differential equation and things of the sort. Yeah.
Yeah, of course, this was before calculus and
yeah, that's the point, that you start with the dynamics and then you imagine about Lagrangians and Hamiltonians. It's only maybe nowadays the one describe the Lagrangian and say which are the equation of motion is the Lagrangian, yeah, something of the sort. Normally is the use of it of the normal. Anyhow, it's like talking by talking. I was not talking very carefully. I was just messing around, giving some ideas. So it's maybe I will shut up for this time.
Oh well. Okay. Are there any
other question, remark?
I want to add to your discussion the principle that, in fact, I don't know if every system of PDEs, but almost every system of PDEs you can find a Lagrangian, but using a trick that consists in adding a lot of extra variables, and you can make a lot of tricks. and the relevant thing of that is that there's another situation where the same equations can be described with different geometries. So if you really want to understand your system, it's not enough to find some geometry that describes your system somehow. It's also the question that finding the right geometry for your system, because then the properties of your geometry will tell you something, important things about the system you are studying. If you put a lot of structure, you have a lot of noise, a lot of virtual particles and things like that that doesn't tell you anything interesting. So just the comment that when you say that there are systems that naturally have a Lagrangian, systems that not, the important thing is that this tell us something about the system, then we can extract information from that.
I mean, when I said that there are systems they don't have a Lagrangian, I meant that on the original manifold you're studying, there is no one. But you know, as you said, you can pick up a system, you can embed it in some other manifold and try to do something there to describe it as a particular example. Okay? Yeah, you can do it. Yeah, the possibilities are infinite, let's say. But as far as I know, what you said is some intuitive. There is, as much as I know, there is no theorem telling you that every second order differential equation can be put in a Lagrangian form by means of an embedding in another manifold. I haven't seen such a thing. But
there are tricks. So you can...
there are tricks in particular, but for particular cases. I mean, if you know that there is some general theorem about how to do it.
No, I don't.
It would be, I would like to know.
Yeah. No, I haven't seen such a theorem. Maybe Jordi, have you seen something like?
I remember Bateman make a lot of things, but I don't know if it was just the physical ones, the polynomials, or just complete in general. I don't know.
Well, that might be interesting to go deeper.
But in any case, the reflection I wanted to make is that it's important to, if you want to understand the system, it's important to not get lost in the geometry. That you have to know what the physics or what are the dynamics that you are trying to study in order to find a geometry that makes sense and not be crazy making a lot of geometry. You have to focus on what are you studying. Just this reflection.
I think it's a good idea, indeed.
Yeah, not getting lost is always a good idea.
That reminds me, a book is Lost in Mathematics, and it's about looking for the beauty of physics, about the structures. Yeah, it says that so far what we have done is just that we have noticed that interesting problems can be described by means of nice geometric theories, but the author says something like it may happen that physics is not that that's beautiful, and indeed at the very end we are getting lost trying to look for some mathematical stuff to describe it, nice mathematical stuff of nice property, when maybe physics doesn't have it. Well, I don't know if it's true or not, but as a book it has it's interesting, yeah, and it's something like Jordi was saying, that maybe we're looking for geometry for a particular problem. Well, one have to think about it, and maybe I will start. We'll stop this topic by myself because I start talking like Urbanski.
But you said before, Javier, what you can do is consider all your equations in a tangent high enough, and then all they are constraints there, and then you take Lagrange multipliers with the Lagrangian equal to 0, and that's it.
When you say high, you say higher order?
High enough, yes. There are people working in
order.
Yeah. I mean, if you have, yes, any kind of PDE, you can put it in an infinite jet bundle and consider the equations as constraints.
Yeah,
and find a Lagrangian there. For instance, you can do this weird thing, but I think it's not very informative. It's what I'm saying.
Listen, I'm not sure about it because I have worked on this. These are called diffeomorphisms, okay? They are infinite dimensional manifolds of a particular stuff. What you said is true. You can prolongate all the jet manifolds, and at the very end, it turns out that certain properties are more useful. For example, the Cartan distribution is integrable in diffeomorphisms. But things become crazy because, for example, there are vector fields which have no integral flows, you know? I mean, they have no integral cubes and things of the sort. So I have to be careful about what
it's enough to go to the jet of the order of your equations. If you go second order equation, second jet.
Well, I should think maybe it's true. I don't know, but I would like to see it written in detail. But it'd be very interesting to see such a thing. If you know, please let me know. I would love to.
Well, what Jordi said is maybe more or less like that theorem, which says that every finite group is a subgroup of a permutation group. So maybe we should only study permutation groups, but nobody studies it like this because it is absolutely crazy. Because that group, I mean, you have to, what's the permutation of n factorial element? I mean, it's absolutely crazy. So nobody studies finite groups like this, and nobody should study Lagrangian mechanics, just adding a lot of dimensions. So that's not the way. I think it's a funny example. So are there any more questions or comments or fun facts or whatever? No? Okay, so maybe we can finish now. It's 10:30. So we'll meet again next Thursday at 9 at the same link. Maybe tomorrow you'll get an email with this recording and the information of the next meeting. We'll finish these lectures on Lagrangian mechanics. And then Jordi will talk the other week. Can you make a spoiler or something like that? Or you don't know?
Yeah, field theories, PDEs.
Oh, great.
And I will try not to kill you with coordinates.
Okay, so multisymplectic?
I will try to explain some multisymplectic and jet bundles. It's what I have to do. And okay, I don't know with the time I have, I don't know what I want to do, but that's the plan.
Okay, but you can do a second part after
For sure.
Okay.
No one...
2 or 3 weeks afterwards. You can.
Okay, we can do the motivation next
So
week.
count on it. I mean, if you need 2 sessions, you will have 2 sessions.
Okay.
Don't worry. You only have to ask.
We
And
will give
send
you
the
as
app.
much...
Okay.
Well,
Send you the access.
we can finish recording maybe at this point.
Yeah, maybe we can finish. Okay.